Okay, in the previous video we derived the Laplace's equation, right? Or we derived Laplace's equation, which is shown here, right? And we said that solving this equation using the boundary conditions or the initial conditions for the problem in question, in the case of seepage through soil or seepage in soil, the case is that of having boundary conditions to be able to solve this equation for a particular problem. Well, we said that if we are able to solve this equation, we would get essentially an equation that is like this. Sorry. We would get the head at any point, the point given, of course, by the coordinates x and z. What point? Well, or which points? Well, the points that are associated to the geometry of the seepage, right? So, for example, if the problem looks like this, okay, forget about these lines or curves for now. Just think about the fact that here's the bedrock, this is soil, here's the ground surface, here's a wall, right, inserted in the ground. Here's the downstream side and the upstream side. And essentially solving Laplace's equation for this problem would give us the total head at any point. A point here, a point over here, a point here, any point in the soil mass through which seepage is taking place. Okay? So going back to this, just for summarizing, right? We said that if we are able to solve this equation for our particular problem, any problem that we are dealing with, knowing the boundary conditions of that particular problem, we would be able, if we remembered mathematics, we would be able to, of course, solve this equation and get this other equation, which is an algebraic equation, which is h is equal to a function, some function of x and z. Okay? X and z. Now, because we prefer not to go through the math, and because, more importantly, because we prefer to be able to see the geometry of the problem and see the locations of, for example, of high gradient, as we will discuss later, we solve this equation graphically using the Flownets procedure. The Flownets procedure is shown with this example. We're not going to do an example with numbers yet. We're going to just show the different parts of the flownet. Okay? So, let's say again that you have your situation. Your particular situation is one where the wall is embedded into the ground. This is the soil. This down here is rock. Here's the downstream side and the upstream side. Okay? So this wall is meant to retain water on one side, but clearly the water makes it to the other side through the soil. Now, it's important to realize that it says impervious down here. What this means, and you will see it in many books and papers, is that the rock is assumed to have a hydraulic conductivity of 0. Okay? Now, we know that the rock doesn't have a hydraulic conductivity of 0. Typically, rock has a hydraulic conductivity that can be as low as 10 to the minus 15 centimeters per second, or even lower. Because it is so low, we adopt the assumption that it has a hydraulic conductivity of 0. That means that seepage only occurs in the soil mass. Okay, there is no flow through this impervious, meaning no permeability, no hydraulic conductivity material. Okay? Alright, so here's our situation, and the idea is that we would like to know what is the head at any point, right? Okay, so what we would need to do is solve Laplace's equation with the boundary conditions of this problem, and we do so with the Flownets procedure. The Flownets procedure is one that requires you to draw what's called a flow net, okay? And it's very self-explanatory. Is a net or a grid that describes the flow. So here's the grid for this problem, the Flownet. You can see that it's like a mesh, right? It's like a grid. Okay, here are the elements of the Flownet. Okay, and here are the curves that make the Flownet. All right. Now there are two types of curves: the flow line or flow lines and the equipotential lines. Okay. What are flow lines? The flow lines are curves that mark trajectories for water droplets. So for example, if you have a water droplet here, that water droplet is going to flow through the soil along that flow line. If you have one here, that water droplet is going to flow through the soil along this flow line. Okay? Now you may say, what happens if there's a water droplet here? Shouldn't I have another flow line like that? Right? Or what about the water droplet here and here? What about all the water droplets? Well, the idea is that you are going to draw an appropriately drawn flow net, and that requires certain criteria to meet certain criteria, and that's what we're going to talk about later on. For now, we are just defining the curves that make the flow net. Okay? The equipotential lines, they are really curves, okay, are lines or curves along which the total head is the same. Okay? So, here I typically ask the students, how many equipotential lines do we have? I also tell them beforehand that equipotential lines cross flow lines at 90 degrees. Okay? There's intersections between flow lines and equipotential lines. Okay, so students say, for this problem, many students say there are 3. They say, look, there's 1, 2, 3. Okay, and here is where we can make the correction to that mistake. If this is an equipotential line, if we believe that this is an equipotential line, then by definition the head, total head, along this line is the same. Therefore, that means that this point, which is on this equipotential, so-called equipotential line, and this point have the same head. Okay? If this point and this point have the same head, then what does that mean? That means that there is no flow between this point and this point. But clearly there is, because there is a flow line that crosses the 2 points. The water droplet goes from here all around all the way to here. So, what is the answer? Or is it correct to say that this is an equipotential line, this whole thing? No, that's not correct. Because that would mean that this point and this point have the same head. Therefore, that would mean that there is no flow from this point to this point. And clearly, there is flow from this point to this point along the flow line. Okay, so we're going to erase this. And we're going to realize, based on that error correction, that there are 5 equipotential lines here, at least that we can identify for now. 1, 2, 3, 4, 5. Okay? So, along any equipotential line, the total head is the same. Alright, now, a very nice way, I believe, to think of equipotential lines is to think of them as stations along the way of a, let's say, a marathon. Okay? So let's take, for example, the droplet that begins here. This droplet is eventually going to make it here, right? But as it flows through the soil, it loses energy. It loses head. That is why there is a delta H here. Okay? But think of it as a droplet that runs the marathon through the flow line and then exits here. Here's the end of the marathon. At this point, when the droplet gets to this level, the head has has a value, okay? Let's say the head is 10 meters at this point. The water droplet keeps moving, and when it gets to this point, the head may be 8 meters. So it lost 2 meters of energy from this equipotential to this equipotential line. And therefore, you can keep going. You can say, okay, the water droplet is losing energy. Here it has 10, here it's 8, here it's 6, 4, 2, and here it would be 0. But clearly the total head here is not 0. Okay, and we will see that later on when we actually do an example. We'll see that the total head at this point cannot be 0 because there's water above it. But just for the sake of understanding for now what the equipotential line is, you can think of them as stations. Okay, so along the way of a marathon, along the marathon, the person, in this case the droplet that is running, loses energy. Okay, they lose energy, they get to here. At this point they have lost 2 meters of energy. Here they have lost 4, 6, etc. Okay, and you'll see later on with the example, you'll see a little bit better how that works. Okay, so now we have basically described the two types of curves which have the names of lines that make up a flow net. The flow lines, these are trajectories or paths, and the equipotential lines that cross them. Okay? I have said this before, and I will say it again. Some students get confused and think that along a flow line the velocity is equal or is the same. So a point here has the same, the flow at this point has the same velocity as the flow at this point, and has the same velocity as the flow at this point, etc. That is wrong. Okay? That is wrong. The velocity along a flow line may be constant, but it's not necessarily constant. What is the same or constant along an equipotential line, is the total head. Okay? Alright. Now here's another definition. It's called the flow path or flow channel. Okay? And it's basically the channel or path, the road, let's say, between two flow lines. So for example, here's a flow line, here's another flow line. This thing here, this path, this tube, is called a flow path or channel. Okay, that's another definition and we will use it later on. Okay, so here's our problem again. This is the next slide. Here's the water table of the other side. Upstream, downstream, right? The rock down here. Okay, and we said that these are two flow lines and 1, 2, 3, 4, 5 equipotential lines. Now, it is very important once you have your flow net, okay, and ideally you would want to be able to draw the flow net, okay? It's very important as geotech engineers to have some experience in actually drawing a flow net, and you'll see later how we, in the next slide, we're going to talk about how to draw it. But essentially, what we do now in the field is we use computers to draw the flow nets for us because they are more precise than us. They can do it, the computers can do it in shorter time, okay, with less error, etc. But let's say that once you have your flow net drawn or created by the computer, it is very important to identify all the equipotential lines and all the flow lines. Okay, now we have said here that we have two flow lines, but in reality there are four. There are two drawn and two that are so-called hidden, in quotes, okay, hidden. The first one is a flow line that starts at the interface between the soil and the structure. The structure in this case is a wall. So there is a flow line that essentially marks the periphery, okay, of the wall. So imagine a droplet that is right there against the wall. What what is its trajectory going to be? The trajectory is going to be along the wall, down the wall, then around the bottom of the wall, and then up the wall to this point. That is a flow line that we need to account for when we do the calculations with Flownets. So that's one. There's two more that are drawn. And the fourth one, 1, 2, 3. The fourth one is a flow line that starts all the way over here, let's say, and then it goes like this. And it goes along the impervious boundary, the rock. So this here is a flow line. So how many flow lines do we have? 1, 2, 3, 4 in this problem. You'll see that later on we need to use the number of flow lines and the number of flow paths and the number of equipotential lines to be able to solve some of the problems that we're going to solve. So it's important to realize that we need to count these lines. Alright, now as far as equipotential lines, how many? Well, we said before 1, 2, 3, 4, 5 for this problem. But in fact there are two more. They are again hidden, okay? And they're basically listed here. This is the first and this is the last. First equipotential line, last equipotential line, okay? So if you think about it, if you were to put a point here and question yourself and say, I would like to know the total head at this point. You would say, okay, the total head is the elevation head plus the pressure head plus the velocity head, but we neglect the velocity head in geotechnical engineering problems because it's very small. So, what is the total head at this point? To be able to determine the total head at a point, I need the datum, right? And we always use the impervious boundary as the datum. You really don't have to use that as a datum, but that is what we often do. Okay, so you don't have to use the datum at the impervious boundary between that is the boundary between the impervious material, the rock, and the soil, but we often do that. So, what is the elevation head at this point? Well, the distance from the datum to the point. What is the pressure head? The distance from the point to the water table above it. So this whole thing is the total head at this point. Okay? Very simple. Now, if you take this point, the same applies. And if you take this point, the same applies. And if you take that point, same applies. So, along this line, the total head is the same for any point. Therefore, that condition makes this line an equipotential line. And it is the first equipotential. Why? Because that is the beginning of the path for seepage. The soil begins here. Okay? Now, on this side, we have the same situation. If you take a point there, that is the elevation head, and that is the pressure head. And if you take this point, the same applies. Sorry, this whole thing, of course, is the total head here. So if you take this point, that's a total head. If you take this point, that's a total head at that point. The total head at any point is this. So that condition makes this line an equipotential line. Clearly, the head at this point, this, is different than the head at any point on the opposite side of the wall. The head for any point in the upstream side is larger than in the downstream side. That's why there is flow from this point to that point and from this point to that point, etc. Okay? So it's very important to identify the first and last equipotential lines. Now, here, this line here is the last equipotential because this is the end of the soil, or the end of the mass, the outlet of the mass of soil through which seepage is taking place, right? Maybe there is some flow of water in this water column, but we don't, as geotech engineers, we don't really care about that because that's not where the soil is. The soil ends here. We care about the seepage through the soil, the water flowing through the soil layer. Okay, so how many equipotential lines do we have? 1, 2, 3, 4, 5 that are drawn, and then 6, 7. So we have 7. 5 drawn, 2 hidden. For flow lines we have 2 drawn and 2 hidden. That one and that one. Okay, so here is a little explanation of how to draw an appropriate flow net. Okay, how to meet the conditions, the requirements. We're going to take a little part of a flow net, and we're going to take a small piece of a flow net and define different conditions here, different parameters. Here are 2 flow lines, okay? They are parallel to each other, all right? And here are 2 equipotential lines, and they cross the flow lines. Just like here, we have flow lines being crossed by equipotential lines, okay, in this location. So here is just a little part of that. Now the crossings are called nodes, okay? Flow, of course, occurs in the direction parallel to flow lines, okay? And what we are going to say here is that a properly drawn flow net has to have or fulfill two criteria. First, there should be perpendicular crossings at nodes. So at all nodes there should be 90-degree angles, okay? And also there should be something that is often called squarosity, okay, for all elements. An element is a closed geometry, let's say, closed shape that is compounded by by a number of nodes. It doesn't have to be 4 nodes, it could be 3 nodes, it could be 5 nodes, it could be 6 nodes, okay? So don't mistake this word squarosity with a square, okay? It can be the node can be something like this. A node can be something like that, okay? And that's a triangle. The idea is that you should be able to fit a circle in any element, and that circle should touch all sides of the element. So here we have drawn, or the computer in this case has drawn a very nice part of a flow net, because we can, and a properly drawn one, because we can put in here a circle, and the circle touches all sides of this element that has 4 nodes, okay? If we were to have some node that looks like this, then if we can fit a circle in there that touches all sides, then this node is drawn correctly. Okay? Now, drawing, this is something very important, what I'm going to say now. Drawing the flow net correctly is essentially solving Laplace's equation correctly. Okay? So when you draw the flow net in a correct manner, then you have essentially solved Laplace's equation graphically. Okay? That's very, very powerful tool the flow nets are, because they are a solution to Laplace's equation. So let's see how this applies to our flow net, the one that we were analyzing before. Okay, so let's say that we draw this flow net and we say, okay, look, I'm going to have 2 flow lines drawn. I'm going to space them like this, and then I'm going to space my equipotential lines in such a way so that I have somewhat of a nice grid, nice net. Okay, then you come in and say, okay, now let me check if I've done this correctly. You start putting circles in there, in every node, in every element, not every node, every element. So you put this one, okay, that's fine, same as this one, that's good. What about this one here, this little one? That's a triangular element, and it's okay because I can fit my circle in there pretty well, It's well drawn. Same thing here because it's symmetric. This one is fine. Okay. What about this one? Here, if I draw a circle, there's no way I can draw a circle that touches the four sides. So there is a problem. What I need to do is draw the whole thing. Why the whole thing? You may say, well, let's just draw this part around here. Well, what one would do is one would basically try to move this equipotential line in a little bit. But in that case, then you lose squarosity for this element. See that? This circle now doesn't touch this side. So if you try it, and I highly encourage that you try drawing flownets, because that's part of being a geotech engineer, being able to draw flownets in the field. When you don't have a computer at hand, you have to analyze something right there on the spot. You'll realize that you need a very good eraser, because you will make mistakes in drawing the flownet like everybody else, and then when you try to correct those mistakes, you end up making other mistakes somewhere else. So then you have to essentially play around with the flownet until you get some very deep insight into your particular problem, and then you end up with a properly drawn flownet. Another question that often pops up in a student's mind is, well, how many flow lines, if I were to actually draw the flownet, how many flow lines should I have and how many equipotential lines should I have? I mean, I could draw here one more equipotential line, sorry, one more flow line, and then one more here, and I can draw one more here like this. Okay? I could have more. So how do I know how many? Well, in this case, if you decide to draw this many, you would realize that to maintain squarosity, that is to be able to fit this circle, you would have to draw more equipotential lines. Okay? Because if you don't, then you would have these long elements. Okay? Now, the answer to the question is it depends, actually. So it depends on the problem, how many flow lines and equipotential lines you draw. But what matters is the ratio between, or the ratio of equipotential lines to flow lines. Okay? And that is basically, the nice thing about this is that is basically solved, the problem there is solved by keeping squarosity. If you maintain squarosity, which is this, being able to fit the circle in there, then your ratio of flow lines to equipotential lines will be an appropriate one. So, having said that, you could draw a flownet for this problem with two drawn flow lines and 2 hidden ones, and 5 drawn equipotential lines and 2 hidden ones. And another student may draw a flownet with 11 flow lines and 24 equipotential lines, or whatever, right? Well, actually, hold on. If you have 4 to 7, right? Flow lines, equipotential lines. Another student, let's say that this is you, okay? Another student, this is number 1, that's you. Number 2, another student, may draw a flownet with 12 flow lines and 21 equipotential lines. Okay? In this case, the ratio is the same, 4 to 7, right? 4 times 3, 12, 7 times 3, 21. So this ratio is the same as this ratio. If this flow line is drawn correctly, and another person draws this flow line for the same problem, it is very, very likely that you will have the same answers that are engineering answers that you're searching for. Okay? So a properly drawn flownet doesn't require a specific number of flow lines and equipotential lines. What it requires is the proper ratio, and that ratio is maintained or fulfilled when you maintain squarosity. Okay? Generally, we try to draw, depending on the problem, you could draw maybe between 4 flow lines and 10 flow lines, something like that. Okay? Drawing more than 10 flow lines would eventually you would end up with a very fine flownet, and it's very likely that you would make a mistake somewhere when you draw it. that is why essentially at the end we end up using computers to draw our flownets in a very accurate way. But again, it's very important that you have some familiarity with drawing them, because there are times in the field at a site somewhere where you will not have access to a computer and you need answers immediately. Okay, that is the nature of geotech sometimes. Alright, so this is essentially the video on how to, or on what flownets are, and how to not analyze a flownet, but basically count, draw a flownet, let's say, and then count the number of flow lines and equipotential lines that it has. Now we're going to move on to an example.